this point, we know how to take projections if we have an orthogonal basis. We know how to test that something's orthogonal, but we haven't really seen a recipe to build a basis that's orthogonal, so we can use it to find projections on a subspace W. So that's what we'll do now. So how do we take a subspace, or even the entire space, and how do we know that there is an orthogonal basis, and how do we construct it? Well, there's something called the Gram-Schmidt process. And this will start with any basis, let's call them U's, so U1, U2, U, do I want to use UK? Yep, for W. Right, so we know how to find bases for subspaces, so you start with a basis for your subspace, any basis will work, and then you apply the process, you apply the recipe, and what you get in the end, you get an orthogonal basis, V1, V2, Vk for W. Alright, so you start with any basis, you get an orthogonal one, and the steps are pretty straightforward. It might be a bit long if you have many vectors, but it's really a recipe that you could plug into a computer and the computer could do it for you, so it's very, very precise. So let me show you. Alright, so let's say I start with U1, U2, UK. Alright, so I'm going to build my bases V1, V2, Vk one at a time. Alright, so first one. I'm going to take my first vector, V1, to just be U1. Right, it doesn't have any vectors to be orthogonal to yet, so I'm just going to take U1. And I'm going to start doing real work in step 2. So V2 will not be U2 in general. I'm going to start with U2, but I'm going to tweak it so that it's orthogonal to V1. And that's what we did in one of our first examples, where it asks you to find an orthogonal basis for a plane. You start with any basis, you leave the first one as is, but the second one, you take the orthogonal component. So here is U2, I'm going to subtract the projection on U2. So U1, U2, length of, actually let me write V1, it doesn't make a difference here, but that's going to make it more homogeneous, so U2, V1, length of V1 squared V1. Alright, so I'm taking the orthogonal component of V2 perpendicular to V1, so that will be, that will be perpendicular to V1 automatically. Alright, and I keep doing this. I keep taking away all of the projections. So V3 will be U3, but I'm going to take away the projection onto V1. That will make sure that U1 V3 is now orthogonal to V1, and I'm going to do the same thing. I'm sorry, changed the wrong index. I'm going to keep U3. I'm going to take away the projection on V2. Alright, and it's going to keep growing and growing. So for V4, you'll subtract the projection on V1, the projection on V2, and the projection on V3. All right, and the claim at the end. That these vectors that you just constructed, they're orthogonal to each other because of the way we constructed them. And so this is an orthogonal basis for W. Alright, so really there are two different things you need to check. You need to check first of all that the vectors are orthogonal, and I claim that that's the reason why we did this. And the second thing you need to check is that we haven't changed the span. If this is the basis for W, then so will that set of VI's. You'll do that on the assignment. What I want to do now is I want to do an example. Alright, I'm going to look at Euclidean space R3. That means R3 with a dot product. I'm going to find an orthogonal basis by starting with the following basis. So starting with 1, 1, 1, 0, 1, 1, 0, 0, 1, and I want to apply the Gram-Schmidt process to it. So apply the Gram-Schmidt process. Alright, so I have my U1, U2, U3. So we're told to take V1 to be U1. I can put arrows above them because we're in R3. So that's going to be 1, 1, 1. Now V2 will not be U2 because these two vectors are not perpendicular. So I can't use this one. But V2 will be U2 minus the projection. So minus U1 dot U2 dot V1, length of V1 squared, V1. And so that's 0, 1, 1 minus their dot product of the first two here, that'll be 1 plus 1, that'll be 2, divided by the length of V1 squared, so that's 1 plus 1 plus 1 times V1. So I'm getting this minus 2/3 of this. I'll get minus 2/3, 1/3, 1/3. You can check right away that this is orthogonal to your first basis vector, so that's perfect. And now if you remember, just looking at this, this is actually the projection of V1, of V2 in the direction of V1. So the whole thing is the orthogonal component of V2 perpendicular to V1. Right, so that's what we used in our example. But of course, in that example, we only had two vectors. So at that point, we could stop. So we only needed the basic projections that we used in linear 1. But now, let me leave that there. Just I don't want to lose my vector. So V3 is going to be U3 minus U3 dot V1, V1 squared V1, minus U3 dot V2, V2 squared V2. Alright, so U3 is 0, 0, 1. Right, let me erase this now that I've written that vector. And now I'm going to go back and I'm going to use the two basis vector that I've already computed. So for this one, U3 dotted with V1, so that's, let me write it down. So it's 0, 0, 1, 1, 1, 1 over length of 1, 1, 1 squared, 1, 1, 1, minus V2 is this one, so I'm going to take 0, 0, 1 dot minus 2/3, 1/3, 1/3, length of minus 2/3, 1/3, 1/3 squared. Alright, and you can see it gets a bit more complicated. So here I'm getting 0, 0, 1, that part is fine. This is 1 over 3, 1, 1, 1. Here I'm getting a third for this one. This one will be 4/9 plus 1/9 plus 1/9 times V2, which is minus 2/3, 1/3, 1/3. Alright, so we get 0, 0, 1 minus a third, a third, a third, minus, that's 1/3 over 6/9. So that's 9 over 18, that's 1/2. Times minus 2/3, 1/3, 1/3, and I got, that's minus a third plus a third, so that's 0. Let me double check that I haven't messed it up. Now that's fine. All right, so that's fine. And then minus a third, minus a sixth, that's minus a half. Then minus a third, minus a sixth again, that's minus a half, but I have 1 here, so I have plus 1/2. All right, so my new basis is V1, which is 1, 1, 1, V2, which is over here, minus 2/3, 1/3, 1/3, and the final one is right here, 0, minus a half, a half. Sorry about being squished.